Welcome to Sleepy Science Odyssey. Tonight, the universe's scale. The incomprehensible vastness, stretching from the smallest quantum fluctuations to the largest cosmic structures. From subatomic particles measuring 10 to the power of -18 meters, to the observable universe spanning 10 to the power of +26 meters. A range of 44 orders of magnitude, from the Planck length where space itself becomes granular to cosmic voids hundreds of millions of light-years across. From the fleeting existence of virtual particles to the 13.8 billion-year age of the cosmos, from single atoms to galaxy superclusters containing tens of thousands of galaxies, from the density of neutron stars where matter compresses beyond comprehension to the near-perfect vacuum of intergalactic space, from human perception to realms accessible only through mathematics and instrumentation. We'll journey through the scales of existence, exploring how size, distance, time, and mass span ranges that challenge intuition and reveal our place in the cosmic hierarchy. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real cosmology and physics, no exaggeration, just quiet facts in the dark. Let's begin. The observable universe extends approximately 46.5 billion light-years in all directions from Earth, encompassing everything we can in principle observe due to the finite speed of light and the universe's 13.8 billion-year age. The scale of the universe begins with understanding what we mean by observable. Light travels at 299,792,458 meters per second, the cosmic speed limit. In 13.8 billion years since the Big Bang, light has had time to travel approximately 13.8 billion light-years. However, the observable universe extends much farther than this naive calculation suggests, because space itself has been expanding during light's journey. Objects that emitted light 13.8 billion years ago have since moved farther away due to cosmic expansion. Accounting for this expansion, the current distance to the most distant observable objects, the edge of our cosmic horizon, is approximately 46.5 billion light-years, making the observable universe's diameter about 93 billion light-years, or roughly 8.8 times 10 to the power of 26 meters. This observable universe represents merely the portion of the total universe we can access. The universe beyond our cosmic horizon exists, but remains forever unobservable because light from those regions hasn't had time to reach us and never will due to accelerating expansion. The total universe may be infinite in extent. Current observations are consistent with either infinite or finite, but much larger than observable universe. If infinite, the universe contains infinite matter, infinite stars, infinite galaxies, stretching forever in all directions beyond our observational horizon. The most distant observable light comes from the cosmic microwave background, or CMB. The afterglow of the Big Bang released approximately 380,000 years after the universe began, when space first became transparent to light. This radiation has traveled for 13.8 billion years, stretched by cosmic expansion from visible light to microwave frequencies. The CMB defines our cosmic horizon. Beyond it lies the opaque plasma of the early universe. We observe the CMB in all directions, seeing the universe as it was 380,000 years after the Big Bang, when matter and radiation decoupled. Within the observable universe, matter organizes hierarchically into structures spanning vast-scale ranges. Individual stars are separated by light-years. the nearest star to our Sun, Proxima Centauri, is 4.24 light-years, or about 4 times 10 to the power of 16 meters distant. Stars cluster into galaxies containing billions to trillions of stars. The Milky Way, our home galaxy, contains an estimated 200 to 400 billion stars and measures approximately 100,000 light-years, or 10 to the power of 21 meters in diameter. The disk is about 1,000 light-years thick in the stellar regions, with a central bulge several thousand light-years across. Galaxies themselves cluster into groups and clusters. The local group, containing the Milky Way, Andromeda Galaxy, Triangulum Galaxy, and about 80 smaller galaxies, spans roughly 10 million light-years, or 10 to the power of 23 meters. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is approximately 2.5 million light-years distant. It's approaching us at about 110 kilometers per second and will collide with the Milky Way in approximately 4.5 billion years, merging into a single elliptical galaxy that astronomers have nicknamed Milkomeda. Galaxy clusters are among the largest gravitationally bound structures. The Virgo cluster, the nearest large galaxy cluster to the local group, contains roughly 1,300 to 2,000 galaxies and spans about 15 million light-years. At its center lies the enormous elliptical galaxy Messier 87, containing several trillion stars. The Virgo cluster's gravitational influence extends to the local group, pulling it toward the cluster at approximately 300 kilometers per second. This motion combines with cosmic expansion, creating complex dynamics in our cosmic neighborhood. Superclusters represent the next hierarchical level, clusters of clusters. The Virgo cluster forms part of the Laniakea supercluster, mapped in 2014 by Brent Tully and colleagues. Laniakea spans 520 million light-years and contains approximately 100,000 large galaxies with total mass around 10 to the power of 17 solar masses. The name means immeasurable heaven in Hawaiian. The Milky Way lies on Laniakea's outskirts. Mapping superclusters requires measuring galaxy-peculiar velocities, motions relative to cosmic expansion, revealing the gravitational flows defining supercluster boundaries. Yet even superclusters are not the largest structures. The cosmic web consists of galaxy filaments, walls, and sheets surrounding vast voids. Filaments are thread-like concentrations of galaxies stretching hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003, is a cosmic filament extending 1.37 billion light-years, one of the largest known structures. It contains millions of galaxies arrayed in a sheet-like configuration. These structures formed from primordial density fluctuations amplified by gravity over billions of years. Cosmic voids are vast regions of near-empty space between filaments and walls. The largest known void, the giant void in Canes Venatici, spans approximately 1.3 billion light-years and contains far fewer galaxies than typical cosmic volumes. Voids occupy most of cosmic volume, roughly 80%, while filaments and walls where galaxies concentrate occupy the remaining 20%. This foam-like structure reflects initial quantum fluctuations imprinted during cosmic inflation and amplified by gravitational collapse. The cosmic web's structure appears roughly uniform when viewed at sufficiently large scales. Above approximately 300 million light-years, the universe becomes statistically homogeneous and isotropic. This cosmological principle states that the universe looks the same in all directions, and from all locations when averaged over large enough scales. Observations of the CMB and galaxy distribution confirm this principle, supporting models based on the universe's large-scale uniformity despite local lumpiness. Measuring cosmic distances requires multiple methods spanning different scales. For nearby stars within a few hundred light-years, parallax provides direct geometric distance measurements. Earth's orbit provides a baseline. Observing stars from opposite sides of orbit shows apparent position shifts. The shift angle relates to distance through simple geometry. For stars too distant for parallax, standard candles, objects of known intrinsic brightness, allow distance inference by comparing intrinsic and apparent brightness. Cepheid variable stars serve as standard candles for distances up to roughly 100 million light-years. These pulsating stars have periods directly related to intrinsic luminosity. Measuring the pulsation period reveals intrinsic brightness, which compared to observed brightness gives distance. Henrietta Leavitt discovered this period luminosity relationship in 1912, creating a cosmic distance ladder's crucial rung. Edwin Hubble used Cepheids to measure distances to nearby galaxies, revealing that spiral nebulae were actually galaxies far beyond the Milky Way. For greater distances, Type Ia supernovae serve as standard candles. These stellar explosions occur when white dwarfs accrete matter from companion stars, reaching critical mass around 1.4 solar masses, the Chandrasekhar limit, and detonating. The physics of thermonuclear carbon burning in the explosion produces relatively uniform peak brightness, making Type Ia supernovae visible across billions of light-years. Observing these supernovae in distant galaxies allows measuring cosmic expansion history. The cosmic distance ladder combines multiple techniques, each calibrated against the previous rung. Parallax calibrates Cepheids, Cepheids calibrate Type Ia supernovae, and supernovae reach cosmological distances. Uncertainties at each level propagate upward, making distant measurements less precise. Recent improvements, including Gaia satellite parallax measurements and understanding of supernova physics, have refined the distance ladder, though tensions remain between different measurement methods. Redshift provides another distance measure based on cosmic expansion. Light from distant galaxies shifts toward longer wavelengths, red end of the spectrum, because space expands while light travels. The redshift Z equals the wavelength change divided by the original wavelength. For small redshifts corresponding to modest distances, redshift relates simply to recession velocity through Hubble's law. Velocity equals the Hubble constant times distance. For large redshifts approaching Z equals 1 and beyond, the relationship becomes more complex, requiring general relativistic cosmology models. The Hubble constant h0 quantifies the current cosmic expansion rate. Modern measurements give h0 approximately 67 to 73 kilometers per second per megaparsec, where a megaparsec equals 3.26 million light-years. This means galaxies 1 megaparsec distant recede at 67 to 73 kilometers per second on average. The range reflects measurement tensions. Different methods give different values. Local measurements using supernovae indicate higher values around 73, while CMB measurements indicate lower values around 67. Resolving this Hubble tension is a major challenge in cosmology. Cosmic expansion means the universe was smaller and denser in the past. Extrapolating backward leads to the Big Bang, the moment 13.8 billion years ago when the observable universe emerged from an extremely hot, dense state. The Big Bang was not an explosion in space, but an expansion of space itself. All of space participated. There was no center or edge. The early universe was filled with hot plasma that gradually cooled as space expanded, eventually allowing atoms to form, then stars, then galaxies, creating the universe we observe today. The universe's age can be determined from expansion rate and contents. If expansion were constant, age would simply equal the Hubble time, 1 divided by the Hubble constant, approximately 14 billion years. However, cosmic expansion has varied. Early universe expansion slowed due to gravitational attraction of matter and radiation. More recently, expansion has accelerated due to dark energy. Accounting for these effects using observations of supernovae, CMB, and large-scale structure yields an age of 13.799 plus, or minus 0.021 billion years. The scale factor describes cosmic expansion, how distances between freely moving objects change with time. Defining the present scale factor as 1, the scale factor at earlier times was smaller. At redshift z, the scale factor was 1 divided by 1 plus z at redshift z equals 1, corresponding to about 6 billion years ago. The universe was half its current size. At recombination, when CMB formed at redshift z approximately 1100, the universe was roughly 1/1000th its current size. All distances have stretched by factor 1100 since then. Cosmic horizons define observable limits. The particle horizon represents the maximum distance light could have traveled since the Big Bang, accounting for expansion. This gives the 46.5 billion light-year radius of the observable universe. The event horizon represents the maximum distance we will ever be able to see in the future. Due to accelerating expansion, we will never observe events occurring beyond approximately 16 billion light-years from us now. These horizons change with time as the universe ages and expands. Descending through the scales reveals the hierarchy from cosmic to human to atomic, each level spanning orders of magnitude. From the universe's largest structures, we descend through cosmic scales toward the human realm. The journey illustrates how much empty space separates objects and how density varies enormously across the cosmos. Understanding these intermediate scales connects our everyday experience to cosmic vastness and atomic minuteness, showing how humans occupy a middle position in the scale hierarchy, closer to atoms than to galaxy clusters in logarithmic terms. The solar system provides a more comprehensible cosmic scale. The Sun's radius is approximately 696,000 kilometers, or 6.96 times 10 to the power of 8 meters, about 109 Earth radii. Earth orbits at a mean distance of approximately 150 million kilometers, or 1.496 times 10 to the power of 11 meters, defined as 1 astronomical unit, or AU. This distance means light from the Sun takes about 8 minutes 20 seconds to reach Earth. The astronomical unit serves as a convenient distance measure within the solar system. The planetary orbits span vast distances in astronomical units. Mercury orbits at 0.39 AU, Venus at 0.72 AU, Earth at 1.0 AU, Mars at 1.52 AU, Jupiter at 5.2 AU, Saturn at 9.5 AU, Uranus at 19.2 AU, and Neptune at 30.1 AU. Neptune, the outermost major planet, orbits about 4.5 billion kilometers from the Sun, where sunlight takes over 4 hours to arrive. The spacing between planets generally increases with distance, a pattern approximately described by Bode's law, though the law lacks physical explanation and breaks down for Neptune. The Kuiper Belt, containing small icy bodies including dwarf planet Pluto, extends from Neptune's orbit around 30 AU to approximately 50 AU. Pluto orbits at average distance 39.5 AU, with highly eccentric orbit bringing it closer than Neptune at perihelion. The Kuiper Belt resembles the asteroid belt, but is far larger and more massive. It contains hundreds of thousands of objects larger than 100 kilometers and trillions of smaller objects, remnants from solar system formation 4.6 billion years ago. Beyond the Kuiper Belt lies the scattered disk, extending to approximately 100 AU, containing objects with highly eccentric and inclined orbits perturbed by Neptune. Eris, a dwarf planet slightly smaller than Pluto, orbits in the scattered disk at distances ranging from 38 to 98 AU. These distant objects orbit in near darkness and extreme cold, where temperatures hover around 40 Kelvin, 40 degrees above absolute zero. The Oort cloud, a hypothetical spherical shell of icy objects surrounding the solar system, extends from roughly 2,000 AU to perhaps 100,000 AU or even 200,000 AU, nearly halfway to Proxima Centauri. The Oort cloud's inner edge is approximately 1,000 times farther from the Sun than Earth, while its outer edge is perhaps 100,000 times farther. The Oort cloud has never been observed directly. Its existence is inferred from long-period comets, with orbits suggesting they originate from a distant reservoir. The cloud may contain trillions of icy bodies, with total mass several times Earth's mass. Voyager 1, the most distant human-made object, was launched in 1977 and is currently about 159 AU from the Sun as of 2024, traveling at 17 kilometers per second relative to the Sun. It entered interstellar space, the region beyond the Sun's influence where solar wind no longer dominates, in 2012 at about 122 AU. Despite decades of travel, Voyager 1 remains within the solar system's gravitational influence and won't reach the Oort cloud for thousands of years. The probe demonstrates the vast distances even within our planetary system. Interstellar space, the region between stars, has extremely low density. The average density is approximately 1 atom per cubic centimeter, mostly hydrogen. For comparison, sea-level air on Earth contains about 2.5 times 10 to the power of 19 molecules per cubic centimeter. Interstellar space is 10 to the power of 19 times less dense. Most interstellar space is filled with hydrogen and helium from the Big Bang, plus heavier elements created in stars and dispersed by supernovae. Despite its thinness, interstellar matter totals immense mass. Roughly 10 to 15% of the Milky Way's baryonic mass. Molecular clouds, dense regions of interstellar gas where stars form, represent interstellar matter's densest regions, with densities reaching millions of atoms per cubic centimeter in cold cores. These clouds span tens to hundreds of light years and contain masses from thousands to millions of solar masses. The Orion molecular cloud, located about 1,500 light-years away, contains enough material to form thousands of stars. Within such clouds, gravity overwhelms thermal pressure, causing collapse and star formation. Star formation begins when dense molecular cloud cores collapse under gravity. As the core contracts, it heats up and spins faster due to angular momentum conservation. A rotating disk forms around the growing protostar. Planets eventually form from disk material through accretion. Small grains stick together, forming larger bodies, which gravitationally attract more material. This process transformed our solar nebula into the Sun and planets over tens of millions of years, approximately 4.6 billion years ago. Stars themselves vary enormously in size and mass. Red dwarfs, the smallest and most common stars, have masses as low as 0.075 solar masses. Below this, hydrogen fusion cannot sustain, and radii around 0.1 solar radii, or roughly 70,000 kilometers. These stars burn hydrogen so slowly that they can last trillions of years, far longer than the current universe age. No red dwarf has ever died of old age. Blue supergiants at the other extreme can reach 100 solar masses and radii hundreds of times the Sun. Some hypergiants exceed 1,000 solar radii, approaching sizes comparable to Jupiter's orbit. Betelgeuse, a red supergiant in Orion, has a radius approximately 700 times the Sun's radius. If placed at the Sun's position, its surface would extend past Mars's orbit. Despite this enormous size, Betelgeuse contains only about 20 solar masses spread over vast volume, making its average density less than Earth's atmosphere. Betelgeuse will explode as a supernova within the next 100,000 years, an event that will be visible from Earth in daytime. Stellar remnants include white dwarfs, neutron stars, and black holes, objects where normal matter undergoes extreme compression. White dwarfs, the final state for stars like the Sun, pack about 1 solar mass into Earth-sized volume, giving densities around 10 to the power of 9 kilograms per cubic meter, roughly 1 million times denser than water. A sugar cube of white dwarf material would weigh about a ton. Electron degeneracy pressure, quantum mechanical resistance to compressing electrons, supports white dwarfs against gravity. Neutron stars compress even more drastically. A typical neutron star contains 1.4 solar masses in a sphere only 20 kilometers in diameter, about the size of a city. The density reaches 10 to the power of 17 to 10 to the power of 18 kilograms per cubic meter, nuclear density where atomic nuclei touch. A sugar cube of neutron star material would weigh about 100 million tons. Neutron degeneracy pressure, resistance to compressing neutrons, supports neutron stars. These objects are essentially giant atomic nuclei the size of mountains. Black holes represent the ultimate compression. Once matter collapses past the Schwarzschild radius, the distance where escape velocity equals light speed, it forms a black hole from which nothing, not even light, can escape. For a solar mass black hole, the Schwarzschild radius is about 3 kilometers. Stellar mass black holes from supernova collapse typically contain 3 to 20 solar masses. Supermassive black holes at galaxy centers contain millions to billions of solar masses, with event horizons large enough to swallow solar systems. The Milky Way's central black hole, Sagittarius A star or SGR A star, contains approximately 4 million solar masses. Its Schwarzschild radius is about 12 million kilometers, roughly 17 times the Sun's radius, or about 0.08 AU. Despite this enormous mass, the black hole occupies tiny volume compared to the galaxy. The Event Horizon Telescope captured SGR A star's first image in 2022, showing the shadow cast by the event horizon against surrounding hot gas. Galactic rotation demonstrates dark matter's presence through stars moving faster than visible matter alone predicts. The Milky Way rotates differentially. Inner regions orbit faster than outer regions. The Sun orbits the galactic center at about 220 kilometers per second, taking roughly 225 million years per orbit. Since Earth formed 4.6 billion years ago, the solar system has completed about 20 galactic orbits. During each orbit, the Sun oscillates vertically through the galactic disk, crossing the midplane every 30 to 40 million years. Dark matter, detectable only through gravitational effects, comprises approximately 85% of matter in the universe. It doesn't emit, absorb, or reflect light, interacting with normal matter only gravitationally. Dark matter halos surround galaxies, providing gravitational scaffolding that shaped visible structure. The Milky Way's dark matter halo extends far beyond visible stars, perhaps 600,000 light-years, containing 10 times more mass than visible matter. Dark matter's nature remains mysterious. Candidates include weakly interacting massive particles or WIMPs, axions, or primordial black holes. Dark energy represents an even greater cosmic mystery. Observations of distant supernovae in the late 1990s revealed that cosmic expansion is accelerating rather than slowing. This acceleration requires a repulsive force counteracting gravity, dark energy. Dark energy comprises approximately 68% of the universe's total energy density. Its nature is unknown, though it behaves similarly to Einstein's cosmological constant, a constant energy density filling space. Dark energy's effects become significant only at cosmic scales, dominating over matter gravity at distances above hundreds of millions of light-years. The universe's composition by mass energy is roughly 68% dark energy, 27% dark matter, and only 5% ordinary matter, atoms, stars, planets, gas, dust, everything we can see. Of that 5% ordinary matter, most is hydrogen and helium in gas form. Stars comprise less than 1% of the universe's mass. Planets and solid objects are rarer still. We and everything we directly experience represent a tiny fraction of cosmic contents. Zooming inward from cosmic scales to human scales reveals the hierarchy of size. A human being is approximately 1.7 meters tall, a convenient reference scale. We can perceive objects from millimeters to kilometers directly. Below millimeters, we need magnification. Above kilometers, we need travel or instruments to fully appreciate scale. Human scale sits roughly logarithmically between the Planck length at 10 to the power of -35 meters and the observable universe at 10 to the power of positive 26 meters. We're closer to atoms than to galaxies. The tallest human-made structure, the Burj Khalifa in Dubai, reaches 828 meters, roughly 500 times human height. Mount Everest, Earth's highest mountain, stands 8,849 meters above sea level, about 5,000 times human height. Earth's radius is approximately 6,371 kilometers, or 6.37 times 10 to the power of 6 meters, about 4 million times human height. Earth's size places it among the solar system's terrestrial planets, larger than Mercury and Mars, smaller than Venus. Earth's moon has radius 1,737 kilometers, about 1/4 Earth's radius and 1/80th Earth's mass. The moon orbits Earth at average distance 384,400 kilometers, or about 60 Earth radii. This distance is slowly increasing by about 3.8 centimeters per year as tidal interactions transfer Earth's rotational energy to the moon's orbital energy. In the distant past, the moon was closer and appeared larger in the sky. In the distant future, it will recede farther, appearing smaller. The size hierarchy from cosmic to subatomic spans more than 60 orders of magnitude. The universe contains roughly 10 to the power of 80 atoms, a number so large as to be incomprehensible. A human body contains approximately 10 to the power of 28 atoms, mostly hydrogen, oxygen, carbon, and nitrogen. A single cell contains trillions of atoms arranged in complex molecules. Understanding atomic and subatomic scales requires descending through biological, chemical, and ultimately quantum mechanical realms. The biological scales from organisms to cells to molecules reveal hierarchical organization spanning 8 orders of magnitude. Living organisms exhibit remarkable range in size while sharing common cellular and molecular organization. From blue whales to bacteria, life spans more than 8 orders of magnitude in linear dimension while maintaining similar biochemistry. This scale range reflects diverse ecological niches and evolutionary adaptations, with physical constraints including surface area to volume ratios and diffusion limits shaping organism size. The blue whale, Earth's largest animal, reaches lengths up to 30 meters and masses exceeding 150,000 kilograms. Blue whale's enormous size is enabled by water's buoyancy. No land animal could support such mass against gravity. Their size provides advantages, including efficient long-distance travel and protection from predators, but requires enormous food intake. Blue whales consume several tons of krill daily. Size limits exist even for whales. Larger animals would face circulatory and respiratory challenges. The smallest mammals, like Kitty's hog-nosed bat and Etruscan shrew, measure about 3 to 4 centimeters in length and weigh roughly 2 grams. These tiny endotherms face challenges maintaining body temperature. Their high surface area to volume ratio causes rapid heat loss, requiring extremely high metabolic rates. Shrews must eat nearly their body weight daily to fuel metabolism. Below certain sizes, endothermy becomes unsustainable. The smallest warm-blooded animals approach physical limits. Insects span a vast size range from ferroflies less than 200 micrometers, smaller than some protozoans, to beetles and stick insects exceeding 10 centimeters. The smallest insects face challenges including surface tension in water and reduced brain capacity limiting behavior complexity. The largest insects face respiratory limits. Insects breathe through tracheal tubes, directly supplying oxygen to tissues without active pumping. As size increases, diffusion becomes inadequate. Ancient giant insects, when atmospheric oxygen was higher, support this constraint. Single-celled organisms range from bacteria around 1 micrometer to giant amoebas visible to naked eye at several millimeters. Most eukaryotic cells, cells with nuclei, measure 10 to 100 micrometers. This size range reflects constraints on diffusion. Cells rely on diffusion for nutrient and waste transport over intracellular distances. As cells enlarge, surface area increases as the square of linear dimension, while volume increases as the cube, eventually limiting diffusion efficiency. This geometric constraint restricts cell size. Bacteria are typically 1 to 5 micrometers long, with the smallest free-living bacteria around 0.2 micrometers, approaching the theoretical minimum size for autonomous life. Below certain sizes, cells cannot fit necessary molecular machinery, including ribosomes, DNA, and enzymes. The smallest bacteria have streamlined genomes with minimal redundancy. Nanobacteria claimed to be smaller have not been confirmed as living. They may be non-living mineral crystals or dead cell fragments. Viruses, obligate parasites requiring host cells to replicate, range from about 20 nanometers for small viruses like poliovirus to 400 nanometers for giant viruses like mimivirus. Viruses are not considered living. They lack metabolic machinery and cannot reproduce independently. Giant viruses blur boundaries, containing genes suggesting complex ancestry, possibly involving cells. Some giant viruses are larger than the smallest bacteria, challenging simple size-based definitions of life. Within cells, organelles compartmentalize function. Eukaryotic cells contain membrane-bound organelles including nucleus, mitochondria, endoplasmic reticulum, Golgi apparatus, and in plants, chloroplasts. The nucleus, containing genetic material, typically measures 5 to 10 micrometers in diameter. Mitochondria, energy-producing organelles, are approximately 1 to 2 micrometers long, similar to bacterial size, consistent with endosymbiotic origin from ancient bacteria. Chloroplasts measure 5 to 10 micrometers, also bacteria-sized. Ribosomes, the molecular machines synthesizing proteins, measure about 25 nanometers in diameter. Each ribosome consists of ribosomal RNA and approximately 50 proteins, with molecular weight around 2.5 million daltons. A dalton equals 1/12 the mass of a carbon-12 atom. Ribosomes translate genetic information in messenger RNA into amino acid sequences forming proteins. Each cell contains thousands to millions of ribosomes, depending on protein synthesis demands. Proteins, the molecular workhorses performing cellular functions, range from small peptides of a few amino acids to massive assemblies exceeding 2 million daltons. Typical proteins contain 200 to 300 amino acids and measure 5 to 10 nanometers. Titin, the largest known protein, contains about 34,000 amino acids and spans roughly 1 micrometer when stretched, approaching cellular length scales. Titin provides elasticity in muscle tissue. DNA, the hereditary molecule encoding genetic information, has a double helix diameter of about 2 nanometers. The human genome contains approximately 3 billion base pairs. If stretched linearly, it would extend about 2 meters. This enormous length is packaged into the nucleus through hierarchical organization. DNA wraps around histone proteins forming nucleosomes, which coil into chromatin fibers, which further condense into chromosomes. During cell division, chromosomes become maximally condensed, measuring several micrometers, visible under light microscopy. Individual atoms composing biological molecules measure 0.1 to 0.3 nanometers in diameter. Carbon, the basis of organic chemistry and life, has atomic radius approximately 0.07 nanometers for covalent bonds. Hydrogen, the simplest and most abundant element, has radius about 0.025 nanometers. Biological macromolecules assemble from thousands to millions of atoms precisely arranged in three-dimensional structures determining function. The chemical bond, holding atoms together in molecules, has characteristic length around 0.1 to 0.2 nanometers. Carbon-carbon single bonds are approximately 0.154 nanometers long. Carbon-hydrogen bonds are about 0.109 nanometers. Carbon-carbon double bonds are shorter at 0.134 nanometers due to stronger bonding. These bond lengths, determined by quantum mechanics balancing electron sharing and nuclear repulsion, define molecular architecture. Water molecules, essential for life and comprising about 60% of human body mass, measure approximately 0.28 nanometers across. Each water molecule consists of one oxygen atom bonded to two hydrogen atoms in a bent configuration with bond angle about 104.5 degrees. Water's unusual properties, high specific heat, high surface tension, solid phase less dense than liquid, arise from hydrogen bonding between molecules. These properties make water ideal for life's chemistry. Molecular self-assembly creates complex structures from simple components. Cell membranes form from phospholipid bilayers, two layers of phospholipid molecules with hydrophobic tails facing inward and hydrophilic heads facing outward. This arrangement, driven by hydrophobic effect, creates selective barriers separating cellular interior from exterior. Membrane thickness is approximately 5 to 10 nanometers. Proteins embedded in membranes control transport, signaling, and other functions. The spatial organization within cells exhibits fractal-like complexity at multiple scales. Proteins fold into specific three-dimensional shapes. Proteins assemble into multi-protein complexes. Complexes organize into organelles. Organelles fill cells. Cells form tissues. Tissues build organs. Organs constitute organisms. This hierarchical organization, with structure and function emerging at each level, enables biological complexity from molecular interactions. Descending into atomic and subatomic realms reveals the quantum world governing matter at the smallest scales accessible to current physics. Below biological molecules lies the atomic and subatomic realm where quantum mechanics replaces classical physics. Atoms, once thought indivisible, consist of electrons orbiting nuclei composed of protons and neutrons. These particles themselves have internal structure. Understanding subatomic scales requires quantum field theory and particle physics, revealing nature's fundamental constituents and forces down to the Planck length where current theories break down. Atoms measure approximately 0.1 nanometers or 10 to the power of negative 10 meters in radius. Though defining atomic size is tricky, atoms lack sharp boundaries. The atomic radius represents the distance where electron probability density drops to negligible values. Hydrogen, the simplest and smallest atom, has radius about 0.053 nanometers, the Bohr radius. Uranium, among the largest naturally occurring atoms, has radius about 0.175 nanometers. Atoms are almost entirely empty space. Nuclei occupy only about 10 to the power of negative 15 of atomic volume. The atomic nucleus, containing protons and neutrons, measures approximately 10 to the power of negative 15 meters, or 1 femtometer in radius, about 100,000 times smaller than the atom. Despite occupying tiny volume, the nucleus contains over 99.9% of atomic mass. Nuclear density is approximately 10 to the power of 17 kilograms per cubic meter, extraordinarily dense by everyday standards, but typical for nuclear matter. Neutron stars achieve similar densities throughout their volume. Protons and neutrons, collectively called nucleons, each measure about 0.84 femtometers in radius. Protons carry positive electric charge equal in magnitude to the electron's negative charge. Neutrons are electrically neutral. Protons and neutrons have nearly identical masses, about 1,836 times the electron mass. The strong nuclear force binds nucleons into nuclei, overcoming electromagnetic repulsion between protons. This force operates only at femtometer distances, hence atomic nuclei's compact size. Electrons, the negatively charged particles orbiting nuclei, are point particles with no known internal structure. Current experiments place upper limits on electron size below 10 to the power of negative 22 meters, at least 1 billion times smaller than protons. Electrons are fundamental particles belonging to the lepton family. Their mass is approximately 9.109 times 10 to the power of negative 31 kilograms. the lightest massive particle with electric charge. Electrons determine atoms' chemical properties through their quantum states and interactions. Quantum mechanics governs atomic and subatomic behavior. Unlike classical objects with definite positions and velocities, quantum particles exist in superposition states described by wave functions giving probability distributions. Heisenberg's uncertainty principle states that position and momentum cannot simultaneously have precise values. The product of uncertainties is bounded by Planck's constant divided by 4 pi. This fundamental limit prevents classical description of atomic structure. Electron orbitals are regions where electrons have high probability of being found. The Bohr model depicting electrons in planetary orbits is incorrect. Electrons exist in clouds of probability, not definite trajectories. Orbitals have characteristic shapes. S orbitals are spherical, p orbitals are dumbbell-shaped, d orbitals more complex. Electrons fill orbitals following Pauli exclusion principle. No two electrons can occupy identical quantum states, building up the periodic table. Electron transitions between energy levels produce atomic spectra, characteristic absorption and emission of light. When electrons jump between levels, they absorb or emit photons carrying energy equal to the level difference. Hydrogen's spectral lines arise from specific transitions, the Balmer series corresponding to transitions to the second energy level produces visible light lines. Each element has unique spectral fingerprints, enabling identification through spectroscopy. Quarks compose protons and neutrons. Quarks are fundamental particles coming in 6 flavors: up, down, charm, strange, top, and bottom. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up quark. Quarks have fractional electric charges. Up quarks have charge positive 2/3, and down quarks have charge negative 1/3, in units of electron charge. Quarks never exist in isolation. They're always confined within composite particles called hadrons. The strong force binding quarks is mediated by gluons, massless force-carrying particles. Unlike electromagnetism, where force weakens with distance, the strong force increases with separation. Trying to pull quarks apart requires ever-increasing energy. At sufficient energy, quark-antiquark pairs are created from vacuum rather than separating the original quarks. This color confinement explains why individual quarks are never observed. They always form color-neutral combinations. The Standard Model of particle physics describes fundamental particles and 3 of the 4 fundamental forces. Fundamental particles divide into fermions, matter particles including quarks and leptons and bosons, force carriers including photons, W and Z bosons, and gluons. The Higgs boson, discovered in 2012, gives other particles mass through the Higgs field. The Standard Model successfully describes enormous experimental data, but omits gravity and cannot explain dark matter. Fundamental particles are point-like with no known substructure down to current experimental resolution, around 10 to the power of -19 meters, probed at the Large Hadron Collider. Whether particles remain point-like at smaller scales or have internal structure is unknown. String theory proposes that fundamental particles are tiny vibrating strings with length around the Planck length, 10 to the power of -35 meters. Different vibration modes would correspond to different particles. String theory remains speculative without experimental confirmation. Photons, the quantum particles of light and electromagnetic radiation, have no rest mass and travel at light speed in vacuum. Photon energy equals Planck's constant times frequency. Higher frequency photons carry more energy. Visible light photons have wavelengths 400 to 700 nanometers and energies around 2 to 3 electron volts. Gamma-ray photons have wavelengths below 10 picometers and energies exceeding millions of electron volts. Photons mediate electromagnetic force, the interaction between charged particles. Virtual particles are short-lived quantum fluctuations arising from Heisenberg uncertainty in energy and time. Even in vacuum, particle-antiparticle pairs constantly appear and annihilate on timescales inversely related to their mass energy through the energy-time uncertainty principle. These fluctuations have measurable effects, including the Casimir force between conducting plates and contributions to electron magnetic moment. Virtual particles demonstrate quantum vacuum's dynamic nature. The four fundamental forces operate across different scales and strengths. Gravity, weakest but infinite range, dominates at astronomical scales. Electromagnetism, much stronger than gravity with infinite range, governs atomic and molecular structure. The strong force, strongest but confined to femtometer distances, binds nuclei. The weak force, responsible for radioactive decay, operates at even shorter ranges than the strong force. Unifying these forces is a major physics goal. Quantum field theory describes particles as excitations in underlying quantum fields permeating space. The electron is an excitation in the electron field, the photon in the electromagnetic field, and so on. Fields interact through exchange of virtual particles. This framework combines quantum mechanics and special relativity, successfully describing three fundamental forces. Extending quantum field theory to include gravity remains an unsolved problem: quantum gravity. The Planck scale represents the realm where quantum effects and gravity become equally important. The Planck length equals the square root of Planck's constant times Newton's gravitational constant divided by the speed of light cubed, approximately 1.616 times 10 to the power of -35 meters. The Planck time, the time light takes to travel one Planck length, is approximately 5.4 times 10 to the power of -44 seconds. At Planck scales, spacetime itself becomes quantum. The smooth geometry of general relativity breaks down. Quantum foam describes speculative spacetime structure at Planck scales. Just as quantum fluctuations create virtual particles, they might create microscopic black holes, wormholes, and topology changes. Spacetime at Planck scales might be wildly fluctuating and foam-like rather than smooth. These ideas remain speculative. Current physics cannot probe Planck scales experimentally or theoretically describe quantum gravity. Quantum foam represents the current limit of scientific knowledge about spatial scales. The hierarchy problem asks why gravity is so much weaker than other forces. The Planck mass, approximately 10 to the power of -8 kilograms, is the mass scale where gravitational and quantum effects balance. This is about 10 to the power of 19 times heavier than the proton. Particle physics operates at energies far below Planck's scale. Why is there such a huge gap? Various theories, including supersymmetry and extra dimensions, attempt to explain this hierarchy, but the problem remains unresolved. String theory proposes additional spatial dimensions beyond the familiar 3. In some versions, there are 6 or 7 extra dimensions compactified, curled up, at scales around the Planck length or slightly larger. These hidden dimensions would be invisible because they're too small to detect directly. Extra dimensions could explain hierarchy problems and provide candidates for dark matter and dark energy. However, string theory lacks experimental predictions testable with current technology. Loop quantum gravity, an alternative quantum gravity approach, suggests spacetime has discrete structure at Planck scales. Space is quantized into indivisible units. Rather than smooth continuum, spacetime would be network-like with nodes and edges representing quantized geometry. This approach attempts to reconcile general relativity and quantum mechanics without requiring extra dimensions or strings. Like string theory, loop quantum gravity currently lacks experimental tests. Timescales from the Planck time to the universe's age span an incomprehensible range of more than 60 orders of magnitude. Just as spatial scales span vast ranges, temporal scales from the briefest quantum fluctuations to cosmic evolution encompass extraordinary range. Time intervals from 10 to the power of -44 seconds to 10 to the power of 18 seconds represent a spread comparable to spatial scales from Planck length to the observable universe. Understanding temporal hierarchy illuminates processes from particle physics to cosmology, showing how phenomena at different timescales emerge from faster underlying dynamics. The Planck time, approximately 5.4 times 10 to the power of -44 seconds, represents the shortest meaningful time interval in current physics. It's the time light takes to travel one Planck length. Below the Planck time, quantum gravitational effects dominate and spacetime itself becomes uncertain. No theory describes physics below Planck time. This represents a fundamental limit to temporal resolution, just as the Planck length limits spatial resolution. Events briefer than Planck time may be physically meaningless. The timescales of particle physics span attoscons, 10 to the power of -18 seconds, to yoctoscons, 10 to the power of -24 seconds. The strong force acts on timescales around 10 to the power of -23 seconds, the time light crosses a proton. Quarks exchange gluons and interact on these timescales. Weak force interactions, responsible for certain radioactive decays, occur on slightly longer timescales around 10 to the power of -13 seconds. Electromagnetic processes, including electron transitions, happen on femtosecond, 10 to the power of -15 second, to attoscon timescales. Attoscon science, enabled by laser technology producing attoscon light pulses, observes electron motion in atoms and molecules. Electrons orbit hydrogen atoms on timescales around 150 attoscons, determined by dividing orbital circumference by electron velocity. Molecular vibrations occur on femtosecond timescales. Observing these fast processes requires even faster measurement tools. Attoscon pulses allow filming electron dynamics, revealing quantum behavior in real time. Radioactive decay provides natural clocks spanning enormous timescale ranges. Some isotopes decay in microseconds, while others persist for billions of years. Half-life, the time for half the atoms to decay, characterizes each isotope. Carbon-14 has half-life 5,730 years, useful for dating organic remains up to about 50,000 years old. Uranium-238 has half-life 4.5 billion years, nearly equal to Earth's age, enabling geological dating. The variation in half-lives reflects different decay mechanisms and nuclear structure. Biological timescales span from nanoseconds for molecular vibrations to centuries for organism lifespans. Enzyme reactions typically complete in milliseconds to seconds. Neural action potentials, electrical signals in neurons, last about 1 millisecond. Heartbeats occur every second or so in humans. Circadian rhythms follow roughly 24-hour cycles. Human lifespans extend to approximately 100 years. Bristlecone pines live over 5,000 years. Biological time perception operates at human scale. We directly perceive events from milliseconds to years. Geological time extends from thousands to billions of years. Continental drift proceeds at centimeters per year, about the rate fingernails grow. Over millions of years, this creates ocean basins and mountain ranges. Erosion wears mountains down at similar rates. The rock cycle, formation, uplift, erosion, and recycling operates on tens to hundreds of millions of years. Plate tectonic configuration changes dramatically over hundreds of millions of years, periodically assembling and breaking apart supercontinents. Earth formed approximately 4.54 billion years ago from the solar nebula. The oldest rocks on Earth date to about 4.0 billion years. Earlier rocks were destroyed by geological activity. The oldest minerals, zircon crystals, date to 4.4 billion years, indicating liquid water existed then, earlier than previously thought. The Hadean Eon, Earth's first 600 million years, saw heavy bombardment by asteroids and comets, with possible early oceans evaporating and reforming repeatedly. Life emerged between 3.5 and 4.0 billion years ago, based on fossil and chemical evidence. The earliest confirmed fossils, stromatolites formed by bacterial mats, date to 3.5 billion years. Chemical signatures in older rocks suggest life may have existed 3.8 to 4.0 billion years ago. Life appeared relatively quickly after Earth became habitable, suggesting either that life forms readily from chemistry or that it arrived from elsewhere, panspermia. Simple single-celled life dominated for billions of years. Complex multicellular life appeared relatively recently. The Cambrian explosion approximately 540 million years ago saw rapid diversification of animal body plans. Before this, life was mostly microscopic for 3 billion years. The oxygen-rich atmosphere created by photosynthetic bacteria over billions of years enabled complex life's emergence. Mass extinctions punctuated evolution, the largest at the Permian-Triassic boundary 252 million years ago, killing over 90% of species. Dinosaurs dominated from about 230 to 66 million years ago. Their extinction 66 million years ago, likely caused by asteroid impact, enabled mammals' rise. Primates emerged about 60 million years ago. The human lineage diverged from chimpanzees approximately 6 to 7 million years ago. Anatomically modern humans appeared about 300,000 years ago. Civilization began roughly 10,000 years ago. The entirety of human history represents about 0.002% of Earth's age. Stellar lifetimes depend on mass. Massive stars burn bright and die young. Stars 10 times solar mass live only tens of millions of years before exploding as supernovae. The Sun, a medium-mass star, has lifetime approximately 10 billion years. It's currently 4.6 billion years old, roughly middle-aged. Red dwarfs, the smallest stars, can live trillions of years, far longer than the current universe age. No red dwarf has yet reached the end of its life. The least massive stars will outlive all others. The Sun will exhaust core hydrogen in about 5 billion years, swelling into a red giant and likely engulfing inner planets, including Earth. After shedding outer layers as a planetary nebula, it will leave behind a white dwarf that will cool and fade over trillions of years. Earth's habitability will end sooner, within a billion years. Increasing solar luminosity will cause runaway greenhouse effect, evaporating oceans and sterilizing the planet. complex life may have only a few 100 million years remaining. Galactic timescales exceed stellar lifetimes. The Milky Way formed about 13 billion years ago, soon after the Big Bang. It has undergone many mergers with smaller galaxies. Evidence remains in tidal streams of stars. The collision with Andromeda in 4 to 5 billion years will reshape both galaxies over billions of years, eventually forming a merged elliptical galaxy. Individual stars rarely collide due to vast stellar spacing. Stellar orbits will be gravitationally perturbed, but stars will pass through each other's space. The universe's far future extends to timescales dwarfing current age. Star formation will continue for tens of trillions of years as hydrogen supplies last. Eventually, gas will be exhausted and star formation will cease. The universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, black holes. White dwarfs will cool over 10 to the power of 15 years. Protons may decay over 10 to the power of 34 years, though this is speculative. Even black holes evaporate through Hawking radiation, the largest black holes in 10 to the power of 100 years. In the extreme far future, if proton decay occurs and black holes evaporate, only radiation and elementary particles will remain, the dark era. If expansion continues accelerating, galaxies beyond the local group will recede beyond cosmic horizon, becoming unobservable. The observable universe will shrink. Eventually, after times vastly exceeding 10 to the power of 100 years, thermal equilibrium at near absolute zero temperature may be approached, heat death. The universe would become cold, dark, and essentially unchanging on observable timescales. Cyclic universe models propose that the universe undergoes infinite cycles of expansion and contraction, avoiding a beginning or end. Current observations suggest eternal expansion rather than future contraction, making simple cyclic models unlikely. However, more complex scenarios, including colliding branes or quantum tunneling to new vacuum states, might allow recurrence over timescales far exceeding 10 to the power of 100 years. These speculations lie at the frontier of cosmological thought. The anthropic principle notes that the universe's properties must be compatible with observers existing to observe them. If physical constants differed even slightly, stars might not form, or chemistry might not allow complex molecules, preventing life. This observation can be explained by multiverse theories. If many universes exist with different constants, we necessarily inhabit one compatible with life. Alternatively, the constants might be uniquely determined by unknown physics. The anthropic principle raises deep questions about coincidence versus explanation. Mass and density span extreme ranges from the lightest particles to supermassive black holes, from the vacuum to neutron stars. Mass, the quantity of matter, ranges over more than 60 orders of magnitude from fundamental particles to galaxy superclusters. Density, mass per unit volume, varies even more dramatically, from the near-perfect vacuum of intergalactic space to the extreme compression of neutron stars and black hole interiors. Understanding mass and density scales reveals the diversity of matter configurations and the physical limits on compression and rarefaction. The electron mass, approximately 9.109 times 10 to the power of negative 31 kilograms, represents the lightest massive particle with electric charge. Neutrinos are lighter, but have tiny masses difficult to measure, less than 1 electron volt divided by c squared, making them at least 1,000,000 times lighter than electrons. The upper limits on neutrino masses from experiments are approximately 10 to the power of negative 36 kilograms. These nearly massless particles were long thought to be exactly massless, but are now known to have tiny but non-zero mass. The proton mass is approximately 1.673 times 10 to the power of negative 27 kilograms, about 1,836 times the electron mass. This mass ratio has profound implications. If it were different, chemistry and thus life would be impossible. The proton mass arises mostly from the strong force binding quarks. The constituent quarks' masses contribute only about 1%. The remaining 99% comes from binding energy via E equals mc squared, demonstrating mass-energy equivalence. The atomic mass unit, or Dalton, defined as 1/12 the mass of carbon-12 atom, equals approximately 1.66 times 10 to the power of negative 27 kilograms, close to the proton mass. Molecular masses range from hydrogen molecule H2 at 2 daltons to biological macromolecules exceeding millions of daltons. Viruses weigh tens to hundreds of millions of daltons. Typical bacteria weigh about 10 to the power of negative 15 kilograms or 1 picogram. Human cells weigh roughly 1 nanogram, 10 to the power of negative 9 kilograms. Human body mass averages around 70 kilograms, a convenient reference point. The largest animals, blue whales, reach 150,000 kilograms. The largest trees, giant sequoias, weigh over 2 million kilograms. Buildings like the Great Pyramid weigh about 6 billion kilograms. Large ships and structures reach tens of millions of kilograms. The largest human constructions barely register compared to natural geological formations. Mountains and geological formations reach immense masses. Mount Everest's mass is approximately 10 to the power of 15 kilograms, roughly 10 trillion times human mass. The total ocean mass is about 1.4 times 10 to the power of 21 kilograms. Earth's atmosphere weighs roughly 5 times 10 to the power of 18 kilograms. Earth itself has mass 5.972 times 10 to the power of 24 kilograms. The Moon is about 1/81st Earth's mass at 7.3 times 10 to the power of 22 kilograms. These planetary-scale masses concentrate enormous gravitational fields. The Sun's mass, approximately 2 times 10 to the power of 30 kilograms, equals about 333,000 Earth masses, or about 1,000 Jupiter masses. Solar mass serves as the astronomical mass unit. Most stars have masses from 0.075 to 100 solar masses. Below 0.075 solar masses, hydrogen fusion cannot sustain, defining the minimum stellar mass. Above about 100 solar masses, radiation pressure from intense fusion overcomes gravity, blowing excess mass away. The Milky Way contains approximately 200 to 400 billion solar masses in stars, plus roughly 10 times more in dark matter, giving total mass around 10 to the power of 12 solar masses, or 2 times 10 to the power of 42 kilograms. The central supermassive black hole contributes about 4 million solar masses, tiny compared to the galaxy's total, but dominating the galactic center's gravitational potential. Most galactic mass resides in dark matter halo, extending far beyond visible stars. Galaxy clusters contain hundreds to thousands of galaxies, with total masses reaching 10 to the power of 15 solar masses, or 2 times 10 to the power of 45 kilograms. Most cluster mass is dark matter. Hot X-ray emitting gas between galaxies contributes more mass than stars. Clusters contain about 6 times more gas than stars. The gas remains hot, around tens of millions of Kelvin, from gravitational compression as matter falls into the cluster potential well. Clusters are the largest gravitationally bound structures. Superclusters and the cosmic web contain even greater masses, though they're not gravitationally bound. Cosmic expansion prevents collapse. The Laniakea supercluster's mass is approximately 10 to the power of 17 solar masses. The total observable universe contains about 10 to the power of 23 solar masses in ordinary matter, roughly 10 to the power of 53 kilograms. Including dark matter increases this by about a factor of 6. Including dark energy, the total mass energy of the observable universe is approximately 10 to the power of 54 kilograms. Density variations across the cosmos are extreme. The density of intergalactic space is approximately 10 to the power of -27 kilograms per cubic meter, roughly 1 hydrogen atom per cubic meter. Interstellar space is denser at about 10 to the power of -21 kilograms per cubic meter. Interplanetary space in the inner solar system has density around 10 to the power of -20 kilograms per cubic meter from solar wind and zodiacal dust. These densities are far below the best laboratory vacuums. Earth's atmosphere at sea level has density approximately 1.2 kilograms per cubic meter. Water has density 1,000 kilograms per cubic meter by definition. A cubic meter of water weighs 1 metric ton. Rock densities range from 2,000 to 3,000 kilograms per cubic meter. Earth's iron-nickel core has density around 13,000 kilograms per cubic meter. The average Earth density is 5,500 kilograms per cubic meter, the highest among solar system planets due to iron core compression. The Sun's average density is about 1,400 kilograms per cubic meter, slightly denser than water. However, density varies enormously from the core, where fusion occurs at densities around 150,000 kilograms per cubic meter, to the outer layers at near vacuum densities. The core temperature reaches 15 million Kelvin and pressure 250 billion atmospheres. These extreme conditions enable hydrogen fusion, converting mass to energy via E equals mc squared. White dwarf densities reach approximately 10 to the power of 9 kilograms per cubic meter, a million times water density. A sugar cube of white dwarf matter weighs about a ton. Electron degeneracy pressure supports white dwarfs' quantum mechanical effect, preventing electrons from occupying the same state. This pressure depends only on density, not temperature, allowing white dwarfs to support themselves even after cooling. The Chandrasekhar limit of 1.4 solar masses is the maximum white dwarf mass. Neutron star densities are approximately 10 to the power of 17 to 10 to the power of 18 kilograms per cubic meter, nuclear density, where atomic nuclei touch. A sugar cube of neutron star matter weighs about 100 million tons. Neutron stars are essentially giant atomic nuclei city-sized. Neutron degeneracy pressure supports them up to about 2 to 3 solar masses, the Tolman-Oppenheimer-Volkoff limit. Above this mass, nothing prevents collapse to a black hole. Black hole density has subtle definition because all mass concentrates at the singularity with infinite density. However, defining density as mass divided by volume inside the event horizon gives surprising results. For stellar mass black holes, average density inside the Schwarzschild radius exceeds nuclear density. However, for supermassive black holes, the average density can be quite low. For a billion solar mass black hole, the average density inside the event horizon is only about 5 kilograms per cubic meter, less than air. This paradoxical result reflects the scaling. Volume grows as mass cubed, while mass grows linearly. The Planck density, approximately 5 × 10⁻96 kilograms per cubic meter, represents the maximum meaningful density in current physics. At this density, quantum gravitational effects dominate. It's the density at which a Planck mass occupies a Planck volume. The Big Bang singularity may have approached Planck density in the earliest moments, though quantum gravity is needed to describe this regime. No current physics describes densities exceeding Planck density. Energy scales from the faintest light to the most powerful cosmic explosions span more than 50 orders of magnitude. Energy, the capacity to do work or cause change, manifests across extraordinary range in the universe. From the lowest energy photons to the most energetic cosmic rays, from the energy content of individual atoms to that of exploding stars, energy scales reveal the diversity of physical processes and the hierarchy of interactions from quantum to cosmic. The smallest energies are measured in electron volts. The energy an electron gains crossing 1 volt potential. 1 electron volt, or EV, equals approximately 1.6 × 10⁻⁻19 joules. Visible light photons have energies around 2 to 3. EV infrared photons have lower energies down to thousandths of an EV. The cosmic microwave background consists of photons with energies around 10⁻⁻³ eV, corresponding to millimeter wavelengths and temperature 2.7 Kelvin. Chemical bonds have energies ranging from about 1 to 10 eV. Carbon-carbon single bonds have energies around 3.6 eV. Carbon-hydrogen bonds are about 4.3 eV. Breaking and forming chemical bonds drives chemical reactions. Photosynthesis uses visible light photons with 2 to 3 eV energy to split water and reduce carbon dioxide, storing chemical energy in sugars. Cellular respiration releases this energy by oxidizing sugars, producing ATP, the cell's energy currency. X-rays have energies from about 100 eV to 100,000 eV. Medical X-rays use energies around 10,000 to 100,000 eV, sufficient to penetrate tissue, but low enough to avoid excessive radiation damage. X-ray astronomy observes high-energy phenomena, including hot gas in galaxy clusters, accretion disks around black holes, and supernova remnants. X-ray energies correspond to temperatures from millions to hundreds of millions of Kelvin via the relation E equals kT, where K is Boltzmann's constant. Gamma rays, the highest energy electromagnetic radiation, have energies exceeding 100,000 eV. Gamma rays from radioactive decay have energies around millions of eV. Gamma ray bursts, the most energetic explosions since the Big Bang, produce gamma rays with billions of eV or GV energies. The Fermi Gamma Ray Space Telescope has detected gamma rays with energies up to hundreds of GV from astrophysical sources, including pulsars and active galactic nuclei. Particle accelerators probe matter at high energies. The Large Hadron Collider, or LHC, accelerates protons to energies around 6.5 trillion eV or TeV per proton. When two counter-rotating proton beams collide, the collision energy reaches 13 TeV. At these energies, new particles can be created from collision energy via E equals mc². The Higgs boson, discovered at LHC in 2012, has mass around 125 GeV divided by c², requiring collision energies exceeding this threshold to produce. Cosmic rays are high-energy particles from space, mostly protons, but including heavier nuclei and electrons. Cosmic ray energies range from millions of eV to beyond 10 to the power of 20 eV, ultra-high energy cosmic rays, or UHECRs. The highest energy cosmic ray ever detected, the Oh My God particle in 1991, had energy approximately 3 times 10 to the power of 20 eV, comparable to the kinetic energy of a baseball traveling 100 kilometers per hour, concentrated in a single proton. The sources of ultra-high energy cosmic rays remain mysterious. Fermi acceleration in supernova remnants can explain cosmic rays up to about 10 to the power of 15 eV. Beyond this, more exotic sources are needed. Perhaps active galactic nuclei, gamma-ray bursts, or new physics. The GZK cutoff, predicted by Greisen, Zatsepin, and Kuzmin, suggests cosmic rays above approximately 5 times 10 to the power of 19 eV should interact with cosmic microwave background photons, limiting the distance they can travel. Observations tentatively confirm this cutoff. Supernovae release approximately 10 to the power of 44 joules of energy, roughly 10 to the power of 51 ergs in traditional units, mostly in neutrinos. This energy comes from gravitational binding energy released during core collapse. A solar mass star converting all its mass to energy via E equals mc squared would yield about 2 times 10 to the power of 47 joules, so supernovae release about 10% of this, still an enormous amount. The visible light from a supernova, though spectacular, represents only about 1% of total energy. Gamma-ray bursts release even more energy than supernovae in brief timescales. Long-duration bursts, lasting more than 2 seconds, likely come from core collapse of massive stars, hypernova or collapsers. Short-duration bursts, lasting less than 2 seconds, likely result from neutron star mergers. The energy release reaches 10 to the power of 44 to 10 to the power of 47 joules within seconds to minutes. If beamed into jets, which observations suggest, the total isotropic energy release could be 100 times lower than inferred from observed brightness. Active galactic nuclei, or AGN, powered by supermassive black holes accreting matter, release enormous energies over extended periods. Quasars, the brightest AGN, can outshine entire galaxies, releasing 10 to the power of 40 watts, 10 to the power of 40 joules per second, continuously. This power comes from gravitational potential energy of infalling matter. As matter spirals toward the black hole, viscosity and magnetic fields heat it to millions of Kelvin, producing intense radiation. Some energy also drives jets of particles to relativistic speeds. The total energy content of the observable universe can be estimated from mass-energy equivalents. The observable universe contains approximately 10 to the power of 54 kilograms of mass energy. Using E equals mc squared with c approximately 3 times 10 to the power of 8 meters per second gives total energy around 10 to the power of 71 joules. Most of this is dark energy, which behaves like vacuum energy with constant density. As the universe expands, the total dark energy increases proportionally to volume, while matter density decreases. The Planck energy, approximately 2 times 10 to the power of 9 joules, represents the energy scale where quantum gravity becomes important. This seems small by cosmic standards, only about the energy in a tankful of gasoline. However, it's the energy concentrated in a single Planck mass particle or Planck volume region. At Planck energy densities, space-time structure breaks down. Early universe during the Planck epoch, the first 10 to the power of negative 43 seconds had temperatures and energies approaching Planck's scale. Vacuum energy, or zero-point energy, arises from quantum fluctuations. Even empty space has energy from virtual particles and quantum field fluctuations. Calculating vacuum energy density from quantum field theory gives absurdly large values, about 10 to the power of 113 joules per cubic meter, compared to the observed dark energy density, around 10 to the power of negative 9 joules per cubic meter. This vacuum energy problem, or cosmological constant problem, is one of physics' greatest unsolved mysteries, with theory and observation differing by 120 orders of magnitude. Temperature spans from absolute zero to the Planck temperature, with each scale revealing different physical regimes. Temperature measures thermal energy, the random kinetic energy of particles. Temperature scales from absolute zero at 0 Kelvin, where quantum mechanical zero-point motion remains but thermal motion ceases, to the Planck temperature around 10 to the power of 32 Kelvin, where known physics breaks down. Understanding temperature scales illuminates thermodynamics, statistical mechanics, and cosmology. Absolute zero, 0 Kelvin or negative 273.15 degrees Celsius, represents the theoretical minimum temperature. At absolute zero, classical thermal motion would cease, though quantum zero-point motion persists. Heisenberg uncertainty prevents particles from being simultaneously at rest and in definite positions. Achieving absolute zero is impossible by the third law of thermodynamics. The lowest temperatures reached in laboratories are billionths of a Kelvin above absolute zero, achieved through laser cooling and evaporative cooling of atomic gases. The cosmic microwave background has temperature 2.725 Kelvin, the coldest naturally occurring temperature in the universe. This radiation fills all space left over from the Big Bang. Interstellar and intergalactic space are slightly warmer due to starlight and CMB absorption. The Boomerang Nebula, a planetary nebula, has gas expanding so rapidly that it cools to about 1 Kelvin, the coldest known natural place. Dense molecular cloud cores can reach a few Kelvin. The triple point of water, where solid, liquid, and gas coexist, occurs at 273.16 Kelvin or 0.01 degrees Celsius. This defines the Kelvin scale. Water freezes at 273.15 Kelvin or 0 Celsius at standard pressure. Room temperature is approximately 293 to 298 Kelvin or 20 to 25 Celsius. Human body temperature is about 310 Kelvin or 37 Celsius. These familiar temperatures correspond to energy scales around 0.025 eV. Thermal energy at room temperature is kT with Boltzmann constant, K approximately 8.6 times 10 to the power of negative 5 eV per Kelvin. Flames and combustion reach temperatures from about 1000 Kelvin for dim red flames to 2000 Kelvin for bright yellow flames to 3000 Kelvin for blue flames. The Sun's surface temperature is approximately 5800 Kelvin, emitting blackbody radiation peaking in visible light, appearing yellow-white. Hotter stars appear blue, cooler stars red. The hottest stellar surfaces exceed 50,000 Kelvin massive O-type stars. Brown dwarfs, too small to sustain hydrogen fusion, have surface temperatures below 2,500 Kelvin. The Sun's core temperature reaches approximately 15 million Kelvin, sufficient for hydrogen fusion. The proton-proton chain converting hydrogen to helium requires these temperatures to overcome electromagnetic repulsion between protons. More massive stars have hotter cores, up to hundreds of millions of Kelvin, where carbon and oxygen fusion occur. Stellar core temperatures determine fusion pathways and ultimately stellar fates. Supernova temperatures reach billions of Kelvin. The core collapse, creating neutron stars, produces temperatures exceeding 10 billion Kelvin. At these temperatures, photons have energies sufficient to create particle-antiparticle pairs. Neutrinos, normally weakly interacting, are trapped and reach thermal equilibrium with matter. The shock wave propagating through the star has temperatures of billions of Kelvin, driving explosive nucleosynthesis, creating elements heavier than iron. Accretion disks around black holes and neutron stars reach temperatures of millions to billions of Kelvin. Matter spiraling inward releases gravitational potential energy as heat through viscosity and magnetic fields. The inner regions of accretion disks around stellar mass black holes reach tens of millions of Kelvin, emitting X-rays. Disks around supermassive black holes in active galactic nuclei can reach similar temperatures in inner regions while extending to vast scales. Particle collisions at accelerators create temperatures exceeding anything in the current universe. The quark-gluon plasma created at RHIC and LHC in heavy ion collisions reaches temperatures around 4 trillion Kelvin, about 250,000 times the Sun's core temperature. At these temperatures, quarks and gluons exist freely rather than confined in protons and neutrons. This state existed in the early universe microseconds after the Big Bang, before cooling allowed hadron formation. The early universe was extraordinarily hot. At 1 second after the Big Bang, temperature was approximately 10 billion Kelvin, hot enough for neutrinos to interact frequently with matter. By 3 minutes, temperature had cooled to about 1 billion Kelvin, allowing deuterium and helium nucleosynthesis. At 380,000 years, temperature was around 3,000 Kelvin, cool enough for atoms to form, allowing light to travel freely, creating the CMB we observe today, cooled to 2.7 Kelvin by expansion. Reheating during cosmic inflation may have produced temperatures around 10 to the power of 15 to 10 to the power of 27 Kelvin, depending on details, high enough to create all particle types in the Standard Model and possibly beyond. The Planck epoch, the first 10 to the power of negative 43 seconds, may have had temperatures approaching the Planck temperature, approximately 1.4 times 10 to the power of 32 Kelvin. At this temperature, thermal energy equals Planck energy, quantum gravity dominates, and spacetime itself becomes quantum foam. No physics describes conditions beyond Planck temperature. Temperature connects to energy via E approximately equal to kT at temperatures of billions of Kelvin. Thermal energy is about MeV, comparable to rest mass energies of electrons and positrons, allowing pair creation. At trillions of Kelvin, energies reach GeV, comparable to proton rest mass. At 10 to the power of 15 Kelvin, energies reach TeV, explored at LHC. At Planck temperature, energies reach Planck energy. This connection allows using temperature to describe energy regimes in particle physics and cosmology. The future evolution of the universe involves temperature decline. As expansion continues, the CMB temperature decreases inversely with the scale factor. In billions of years, it will be below 1 Kelvin. Eventually, after all stars have died and black holes have evaporated through Hawking radiation over 10 to the power of 100 years, the universe will approach zero temperature, the heat-death scenario. The ultimate fate depends on dark energy's nature. If expansion accelerates forever, temperatures will asymptote toward absolute zero. Extreme environments from deepest ocean to highest atmosphere reveal the diversity of conditions on Earth and other worlds. Earth itself exhibits remarkable range in environmental conditions, from crushing depths to thin upper atmosphere, from frigid poles to scorching deserts, from toxic volcanic vents to life-sustaining temperate zones. Comparing Earth's extremes to other planetary bodies shows even greater diversity, from Venus's hellish surface to Titan's hydrocarbon lakes to the interstellar medium's near-perfect vacuum. The deepest ocean point, Challenger Deep in the Mariana Trench, reaches approximately 11,000 meters below sea level. Pressure at this depth is about 1,100 atmospheres or 110 megapascals, over 1,000 times surface pressure. Water temperature is around 1 to 4 degrees Celsius. Despite extreme pressure and darkness, life exists. Amphipods, fish, and microorganisms adapted to these conditions. The pressure would crush most surface organisms, but deep-sea life has evolved specialized proteins and cellular structures. The deepest continental drill holes extend about 12 kilometers, the Kola superdeep borehole in Russia. Temperature increases with depth by approximately 25 to 30 Celsius per kilometer, the geothermal gradient. At 12 kilometers depth, temperature reached about 180 Celsius, limiting drilling. Earth's mantle begins at the Mohorovičić discontinuity, or MOHO, typically 5 to 10 kilometers beneath oceans and 20 to 90 kilometers beneath continents. No drill has reached the mantle. The extreme temperatures and pressures make drilling technologically challenging. Earth's surface atmospheric pressure at sea level averages 101.3 kilopascals, or 1 atmosphere. Air density is about 1.2 kilograms per cubic meter. Most atmospheric mass resides below 10 kilometers altitude. Commercial aircraft cruise at 10 to 12 kilometers, where pressure is about 0.25 atmospheres and temperature around -50 Celsius. The troposphere, where weather occurs, extends to about 10 kilometers at mid-latitudes, higher at the equator, lower at poles. The stratosphere, from roughly 10 to 50 kilometers altitude, contains the ozone layer absorbing ultraviolet radiation. Temperature increases with altitude in the stratosphere, reaching about 0 Celsius at 50 kilometers due to UV absorption. The mesosphere, from 50 to 85 kilometers, cools with altitude to about -90 Celsius at the mesopause, the coldest natural atmospheric temperature. Meteors typically burn up in the mesosphere from atmospheric friction. The thermosphere, from 85 to 600 kilometers altitude, has temperatures rising to 1,500 Kelvin or higher due to solar UV and X-ray absorption. However, the air is so thin, density at 500 kilometers is about 10 to the power of -12 kilograms per cubic meter, that heat transfer is negligible. The International Space Station orbits at approximately 400 kilometers in the thermosphere. Atmospheric drag, though tiny, gradually lowers the orbit, requiring periodic reboosts. The exosphere, above 600 kilometers, is the atmosphere's outermost layer where atmospheric particles can escape to space. Particle density is so low that collisions are rare. Particles follow ballistic trajectories. The exosphere gradually transitions to interplanetary space. Earth's magnetosphere, generated by the planet's magnetic field, extends beyond the atmosphere, protecting against solar wind, a stream of charged particles from the Sun. Venus represents an extreme planetary environment. Surface temperature is approximately 740 Kelvin, hot enough to melt lead, despite Venus receiving only slightly more solar radiation than Earth. The extreme temperature results from runaway greenhouse effect, a thick carbon dioxide atmosphere with sulfuric acid clouds traps heat. Surface pressure is about 92 atmospheres, equivalent to 900 meters water depth on Earth. The atmosphere is so dense that surface winds of a few meters per second exert forces comparable to Earth's strongest hurricane winds. Mars has thin atmosphere, surface pressure about 0.6% Earth's, or 600 pascals. The atmosphere is 95% carbon dioxide. Surface temperatures range from about 130 Kelvin at winter poles to 300 Kelvin at summer equator. The thin atmosphere provides little insulation, allowing extreme temperature swings. Variation of 100 Kelvin between day and night is common. Mars has dust storms that can envelope the entire planet, affecting solar panel power generation for rovers. Jupiter's atmosphere lacks a solid surface. Pressure and density increase continuously until hydrogen transitions to metallic state deep in the interior. Cloud-top temperatures are about 165 Kelvin. Pressure at the cloud tops is about 1 atmosphere. Descending into Jupiter, pressure increases to millions of atmospheres and temperatures reach tens of thousands of Kelvin. The Great Red Spot, a storm larger than Earth, has winds exceeding 400 kilometers per hour, sustained for centuries. Saturn's moon Titan has thick nitrogen atmosphere with surface pressure 1.5 times Earth's. Surface temperature is approximately 94 Kelvin, cold enough for methane and ethane to exist as liquids. Titan has methane rain, rivers, and lakes. The surface receives little sunlight. Saturn's distance from the Sun and Titan's thick hazy atmosphere reduce illumination to less than 1% of Earth's surface. Despite this, Titan has complex atmospheric chemistry producing organic molecules. Neutron star surfaces present the most extreme known stable environments. Surface temperature can exceed 1 million Kelvin immediately after formation, cooling to hundreds of thousands or tens of thousands of Kelvin over thousands of years. Surface gravity is approximately 2 times 10 to the power of 12 meters per second squared, about 200 billion times Earth's gravity. Escape velocity is around 200,000 kilometers per second, 2/3 light speed. Matter at the surface is crushed to nuclear density. The magnetic fields reach 10 to the power of 8 to 10 to the power of 15 Tesla, trillions of times Earth's magnetic field. Inside neutron stars, conditions become even more extreme. Pressure reaches perhaps 10 to the power of 35 pascals, beyond anything achievable in laboratories. Matter exists in exotic states, neutron superfluids, proton superconductors, possibly quark matter in cores. The equation of state, the relationship between pressure and density, at these extremes remains uncertain. Observations of neutron star masses and radii constrain possibilities, but the core composition remains unknown. Black hole event horizons represent event boundaries rather than material surfaces, but conditions near them are extreme. Tidal forces, difference in gravitational pull across objects, become enormous near small black holes. For a solar mass black hole, tidal forces at the event horizon would stretch and compress objects to destruction, spaghettification. However, for supermassive black holes, tidal forces at the horizon can be modest. An infalling observer would cross without immediate trauma, though doom is inevitable once inside. The interior of black holes, beyond event horizons, represents the ultimate unknown. General relativity predicts singularities, points of infinite density and curvature, but quantum effects surely dominate at Planck scales. The singularity might be avoided by quantum gravity, affects creating fuzzballs, gravastars, or other exotic structures. The Penrose diagram for black holes shows that the singularity is in the future time-like direction for infalling matter. The singularity is when you hit it, not where. Understanding black hole interiors requires quantum gravity. The early universe presents extreme conditions unmatched in the present cosmos. During the Planck epoch, temperatures approached 10 to the power of 32 Kelvin, densities approached Planck density, and spacetime itself was quantum. The inflationary epoch may have seen exponential expansion, stretching space faster than light, not violating relativity because space itself expands, not objects moving through space. The quark-gluon plasma filling the universe microseconds after the Big Bang had temperatures trillions of Kelvin. The conditions recreated in particle accelerators like LHC approach, but don't reach early universe extremes. Heavy ion collisions create quark-gluon plasma at temperatures around 4 trillion Kelvin, comparable to conditions 1 microsecond after the Big Bang. However, the volumes are minuscule, perhaps 10 to the power of negative 42 cubic meters, and last only 10 to the power of negative 23 seconds. Future colliders might reach higher energies, probing earlier cosmic epochs, but practical and economic limits constrain what's achievable. Measurement and scale in modern physics reveal fundamental limits and conceptual challenges in understanding the cosmos. The ability to measure and comprehend vast-scale ranges represents one of humanity's greatest intellectual achievements. From direct sensory perception limited to human scale, we've extended reach through instruments and mathematics to realms from Planck length to cosmic horizon. Yet fundamental limits exist: quantum uncertainty, cosmic horizons, computational complexity, preventing complete knowledge. Understanding these limits reveals deep truths about nature and measurement. The Planck units define natural scales, combining fundamental constants: Planck's constant, Newton's gravitational constant, and light speed. Planck length equals approximately 1.616 times 10 to the power of negative 35 meters. Planck time equals approximately 5.4 times 10 to the power of negative 44 seconds. Planck mass equals approximately 2.2 times 10 to the power of negative 8 kilograms, surprisingly macroscopic. Planck temperature equals approximately 1.4 times 10 to the power of 32 Kelvin. These scales mark where quantum gravity effects become important and where current physics breaks down. Heisenberg's uncertainty principle sets fundamental limits on measurement. Position and momentum cannot simultaneously have precise values. Delta x times delta p is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2 pi. Energy and time have similar uncertainty relation. These aren't limitations of instruments but fundamental properties of nature. The more precisely position is measured, the less precisely momentum can be known, and vice versa. The measurement problem in quantum mechanics asks what happens during measurement. Before measurement, quantum systems exist in superposition of states. Measurement yields definite outcomes. The transition from superposition to definite state, wave function collapse, is not described by the Schrödinger equation. Various interpretations, Copenhagen, many worlds, de Broglie-Bohm, attempt to resolve this. The measurement problem remains debated after nearly a century of quantum mechanics. The holographic principle suggests that all information in a volume of space can be encoded on the boundary surface. This idea emerged from black hole thermodynamics. Black hole entropy is proportional to horizon area, not volume. The holographic principle might imply the universe has fewer degrees of freedom than naively expected. Perhaps space is fundamentally two-dimensional, with three-dimensional being emergent. This principle challenges conventional understanding of space and information. Information theory provides another perspective on scale. The Bekenstein bound limits information in a finite region with finite energy. The maximum entropy is 2 pi times energy times radius divided by h bar c for the observable universe. This gives approximately 10 to the power of 123 bits of information. This seems vast, but is finite. The bound suggests the observable universe contains finite information content despite possibly infinite extent beyond our horizon. Computational limits constrain simulation and prediction. The universe has existed finite time with finite speed of information propagation, limiting how much computation could have occurred. Seth Lloyd calculated that the observable universe could have performed at most 10 to the power of 120 operations on 10 to the power of 90 bits, finite though enormous. This limits how complex structures could have formed and suggests the universe cannot simulate itself faster than it evolves. Chaos theory reveals fundamental limits to prediction even in deterministic systems. Sensitive dependence on initial conditions means tiny measurement uncertainties grow exponentially, limiting prediction horizons. Weather is predictable days ahead, not weeks. N-body gravitational systems become unpredictable over timescales of Lyapunov times. The solar system's Lyapunov time for planetary orbits is about 5 million years, limiting long-term prediction despite deterministic physics. The cosmic horizon limits what we can observe and interact with. Light from beyond approximately 46.5 billion light-years hasn't reached us. Due to accelerating expansion, we'll never receive light from regions currently beyond about 16 billion light-years, the event horizon. Objects beyond this recede faster than light due to space expansion. We're causally disconnected from beyond our horizon. No signal or influence can cross it. The observable universe is finite regardless of total universe size. Dark matter and dark energy represent 95% of cosmic mass energy but remain mysterious. Dark matter affects visible matter gravitationally but doesn't emit light. Candidates include WIMPs, axions, primordial black holes, none confirmed. Dark energy drives accelerating expansion, but its nature is unknown. It might be Einstein's cosmological constant, a dynamical field, or modified gravity. These unknowns mean our understanding of universe composition is fundamentally incomplete. The fine-tuning problem notes that physical constants seem precisely adjusted for life. If the strong force were slightly weaker, nuclei wouldn't form. If slightly stronger, hydrogen would be rare. If electromagnetic force were different, chemistry would be impossible. Possible explanations include multiverse. We inhabit a life-compatible universe among many, or unknown physics determining constants. The fine-tuning problem shows we don't understand why constants have observed values. Dimensional analysis reveals deep structure in physics. Physical quantities have dimensions: length, mass, time, charge. Equations must be dimensionally consistent. Both sides must have same dimensions. Fundamental constants like c, h, g have dimensions linking different quantities. The Planck units form these constants into natural scales. Dimensional analysis allows deriving relationships without detailed calculations and checking whether proposed equations make sense. Orders of magnitude estimation enables quick approximate answers. Rather than exact calculation, estimate answer within factor of 10. For example, how many piano tuners in New York? Estimate population, fraction owning pianos, tuning frequency, tunings per tuner per year. Multiply estimates getting order of magnitude. Such Fermi problems, named after Enrico Fermi who excelled at them, develop intuition for scales and feasibility. The cosmic distance ladder demonstrates how science extends knowledge beyond direct measurement. Each rung calibrates the next. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae reach cosmological distances. Systematic errors can propagate and compound, but independent methods cross-check. The distance ladder exemplifies how careful methodology extends understanding across enormous scale ranges. Logarithmic scales prove essential for representing vast ranges. Plotting magnitude versus distance on linear scales is impractical. Distances from meters to 10 to the power of 26 meters span unrepresentable range. Logarithmic scales compress range. Each tick represents multiplication by 10 rather than addition of constant. Decibels for sound, astronomical magnitudes, pH for acidity, Richter scale for earthquakes, all use logarithmic scales for managing large ranges. The scale-free nature of fractals illustrates that some phenomena lack characteristic scales. Fractal dimension, self-similarity, power laws, these features appear across scales from particle physics to cosmology. The cosmic web has fractal-like structure. Turbulence shows cascade across scales. Biological branching, bronchi, arteries, trees, exhibits fractal patterns. Scale-free structure suggests that simple rules can generate complexity across all scales. Human intuition evolved for human-scale environments. We intuitively grasp distances from millimeters to kilometers, times from seconds to years, masses from grams to tons. Beyond these ranges, intuition fails. Quantum mechanics seems bizarre because evolution didn't prepare brains for atomic scales. Cosmic scales seem incomprehensible because we never encountered them. Mathematics extends thinking beyond intuition, allowing rigorous reasoning about realms we can't directly experience. If you're still awake somewhere in this journey through scales, from the quantum foam to the cosmic web, from attoscons to eons, from electrons to superclusters, there's more to contemplate about your place in the hierarchy of existence. But if sleep has found you, if consciousness has faded into dreams, rest knowing that right now you exist at a unique position in the scale spectrum, neither impossibly small nor unimaginably large, but at a scale where structure and complexity enable awareness itself. You occupy roughly the geometric mean between atoms and galaxies on a logarithmic scale. A human is about 10 to the power of 0 meters, 1 meter tall. The Planck length is 10 to the power of negative 35 meters. The observable universe is 10 to the power of positive 26 meters. On a log scale from Planck to cosmos, humans sit close to the middle. This isn't coincidence. Consciousness requires certain scale. Too small and quantum uncertainty dominates. Too large and communication delays prevent coherent thought. You exist at the scale where complex chemistry enables complex cognition. Your body contains about 10 to the power of 28 atoms, an incomprehensible number, yet infinitesimal compared to the universe's 10 to the power of 80 atoms. Those atoms cycle through you. Carbon atoms you breathe out were recently in your body, before that in food, before that in plants or animals, before that in ancient sea creatures, before that in stars. You're made of recycled stardust, temporarily assembled into conscious configuration. In years or decades, those atoms will disperse, forming other structures in nature's endless recycling. Your lifetime of decades spans infinitesimal fraction of cosmic time. The universe existed 13.8 billion years before you, and will exist perhaps forever after. Your conscious experience occupies perhaps 10 to the power of 18 seconds, a trillion seconds if you live 100 years. The Planck time is 10 to the power of negative 44 seconds. The current cosmic age is 10 to the power of 18 seconds. Future cosmic evolution extends to 10 to the power of 100 years or 10 to the power of 108 seconds and beyond. You exist in the universe's first moments on cosmological timescales, yet your experience is unique and irreplaceable. Of all possible configurations of matter, the specific arrangement forming you exists only briefly in only one location. Your particular conscious experience, your memories, thoughts, sensations, occur nowhere else. The vast cosmos contains everything but experiences nothing. You're one of perhaps trillions of consciousness instances throughout cosmic history, each unique, each experiencing the universe from one perspective. The scales you've journeyed through tonight, from Planck to cosmos, all exist simultaneously. Right now, quantum fluctuations occur at Planck scales in every atom of your body. Right now, the cosmic microwave background photons that have traveled 13.8 billion years are arriving at your location. Right now, galaxies billions of light-years distant are emitting light that will travel eons before potentially reaching Earth long after humanity is gone. All scales coexist, nested within each other. Physical law appears the same across all accessible scales. The same quantum mechanics governing atoms governs molecules and bulk matter. The same gravity bending light around the sun holds galaxies together. The same electromagnetic force binding atoms together propagates across cosmic distances. This universality of law, confirmed across 40 orders of magnitude in distance and 60 orders in energy, suggests deep unity underlying apparent diversity. Yet mysteries remain at the extremes. Quantum gravity, unifying quantum mechanics and general relativity, remains unsolved. Dark matter and dark energy comprise 95% of the universe, yet remain unidentified. The Planck scale and early universe hide behind current theory's limits. The far future beyond 10 to the power of 100 years involves physics we can only speculate about. Human understanding, though vast, remains incomplete and perhaps will always remain so. Your mind, a pattern of neural activity in 1.4 kilograms of brain tissue, contemplates scales from 10 to the power of negative 35 to 10 to the power of positive 26 meters, 61 orders of magnitude. This extraordinary reach of comprehension, achieved through mathematics and measurement, represents perhaps consciousness's most remarkable capacity. You can hold both the infinitesimal and infinite in thought, transcending perceptual limitations through abstraction and reason. The quest to understand scale continues. Future telescopes will probe deeper into space and time, perhaps finding the first stars or detecting gravitational waves from the Big Bang. Future accelerators might reach higher energies, revealing physics beyond the standard model. Future theory might unify forces or explain constants' values. Each advance extends understanding, yet each answer raises new questions. The frontiers recede infinitely. Contemplating cosmic scales often produces feelings, awe at vastness, humility at human smallness, wonder at existence itself. These emotions, though subjective, reflect genuine encounter with reality's scope. The universe is unimaginably large, yet we can imagine it, a paradox of consciousness. Your capacity to feel insignificant reflects understanding of significance, itself a form of cosmic self-awareness. Perhaps the universe's scale serves purpose beyond physics. If consciousness requires certain scales, complex enough for chemistry, small enough for communication, then vast universe enables rare instances of awareness. Stars must live billions of years for heavy elements to form and for life to evolve. Galaxies must be large for sufficient star formation. The universe must be old and vast for observers to exist. Your existence constrains cosmic properties through the anthropic principle. The journey through scales reveals unity in diversity. From quarks to galaxy superclusters, matter organizes hierarchically, each level emerging from lower levels yet exhibiting new properties, emergence. Atoms combine into molecules with chemical properties absent in constituent atoms. Molecules form cells with life properties absent in molecules. Cells form organisms with consciousness absent in cells. Each scale reveals new phenomena irreducible to components. This hierarchical organization might continue beyond current knowledge. Perhaps atoms are composite at Planck scales. Perhaps the universe is part of multiverse hierarchy. Perhaps consciousness participates in scales we don't yet comprehend. The history of science shows repeated discovery that apparent fundamentals are composite, molecules made of atoms, atoms of particles, particles of quarks. Where this ends, if it ends, remains unknown. The cosmic perspective, seeing humanity and Earth from universal scale, can transform values and priorities. Pale blue dot photos from space show Earth as tiny speck in cosmic vastness. National boundaries invisible, conflicts seem parochial, common humanity apparent. Yet this perspective risks nihilism. If we're insignificant, does anything matter? The answer is nuanced. We're insignificant to the cosmos, but significant to ourselves, and that's enough. Meaning is local even if universe is vast. Scale awareness cultivates intellectual humility. Our direct experience covers tiny scale range. Most of reality, from quantum to cosmic, lies beyond perception. What seems obvious at human scale, continuity of matter, arrow of time, 3 spatial dimensions, may be illusions or approximations. True reality might differ profoundly from appearance. Accepting this uncertainty while pursuing understanding balances confidence and humility. The universe's comprehensibility, despite vast scales, remains profound mystery. Why should human minds, evolved for savanna survival, comprehend quantum fields and cosmic expansion? Eugene Wigner called this the unreasonable effectiveness of mathematics. Perhaps the universe's mathematical structure makes it comprehensible in principle. Perhaps intelligence naturally grasps patterns that exist. Perhaps we anthropomorphize, imposing patterns that aren't really there. The mystery of comprehensibility rivals the mystery of existence. Your thoughts tonight have spanned scales from smallest to largest, briefest to longest, lightest to heaviest. You've traveled mentally further than you could physically traverse in lifetimes. This journey, though abstract, reflects real exploration, genuine engagement with universe's structure through reason and evidence. The quest to understand scale continues in laboratories and observatories, telescopes and accelerators, equations and experiments. See you next time.